This problem begins with the object having translational velocity, v naught, but currently omega equals 0, or omega naught equals 0. So we're going to start with that information. Is that good for you guys? When it reaches this point, the blue line, this is t equals 0. This is the moment that it is experiencing a frictional force. And because it's not spinning at all, once it reaches that point, it experiences a frictional force in this direction, and this has to be kinetic friction. It's actually experiencing two other forces. I don't know that I need to draw them in there. mg downwards, normal force upwards. Do you need me to draw them all? All right, so are we pretty confident that with our prior knowledge from first semester, we can indicate that the frictional force is going to be equal to mu k mg? All right, so this problem can be solved more than one way. I am choosing to solve it using forces and then motion equations. It can be solved using the work-energy theorem as well, but I don't know that it's as straightforward. It's all the same amount of work. So it doesn't simplify our work to do it the other way. So I'm going to do it as a net force problem and net torque problem, okay? So I will start by saying the net force on the system equals ma, and I'm talking about the x direction. To the right is considered the positive direction, so I'm going to intentionally indicate that the friction is negative and that equals ma. I just thought there was a problem. Since we know the frictional force is equal to mu k mg, I can kind of immediately do some quick substitutions. Mu k mg equals ma, and therefore a equals negative mu k g. What I'm setting up here is I'm setting up the fact that we know that the object's initial velocity, v naught, is getting smaller and smaller and smaller. And it's getting smaller by this amount every second, right? This is the acceleration of the object. So our initial velocity is v naught at time 0. And we know that eventually the object's going to have some future velocity, v final. That's when it's rolling, correct? And at that point, we would like to know how far it traveled or how long it took for that to happen. These are the five motion variables associated with this problem. This question asked for D. It wants to know how far does the object travel getting to a point where it's rolling. Well, we don't have enough. All we have is the initial velocity and an expression for the acceleration. In order to solve for a problem, we need to have 3 pieces of information. We only have 2. Or solve for a motion problem, we'd have 3 pieces of information. We only have 2. So let's look at other information we have. This unbalanced force is also an unbalanced torque. If I consider that that is a torque about the center of mass of the object, then I could write that the net torque is equal to I alpha. Now, this friction causes a positive torque because it's causing the object to roll in the positive direction relative to the positive direction being to the right. But I do also need to recognize that torque requires 3 pieces of information in order to calculate an individual torque, and we have those. So the torque is going to be the radius of the object times the kinetic friction, and that's going to equal whatever the moment of inertia of the object is times alpha. Good so far? All righty. Well, I can write this as R mu k mg equals I. And since we are going to be going to the point where it's rolling, I think we can also make the final statement, which we're going to need here, which is eventually we know that V final has to equal omega final times R. That's the condition for rolling, right? So when we're trying to figure out the conditions for rolling, those are they. Now, since we know we're going to get to a state of rolling, when it is rolling, we'll be able to write this as A over R. Now, the problem is that substitution seems reasonable now because we know we're going to get to a state of rolling. But can we make that substitution while we're going from here to here? All right, so that's the first mistake I see a lot of people make. That will be okay when we're rolling. But during the time where we're transitioning, we're not going to be able to do that. Or have to leave it as alpha. So that leaves us here, R mu k. Well, it's already written. So I'm going to go ahead and solve this for alpha. But I'm going to organize it a little differently than it's organized there. I'm going to put the M and R together with the I. And then I'm going to leave the mu k and g apart. I know I'm leaving it in terms of I, but I know that no matter what, my rolling object is going to have a moment of inertia that will have an mr squared term in it. You guys follow why I'm doing it this way? So by grouping it that way, I know that that's just going to end up being a term that has r in it at the end of the day, and some number that represents the portion of the moment of inertia for that particular shape. So 2/5, 1/2, 2/3, whatever. Now, the difference here is that this is my acceleration. My initial angular speed is 0. I know it's going to have a delta theta. I know it's going to have a final velocity, and I know it's going to have some time. Those are the motion variables associated with it. I only know 2 of them again. But I do know something else, and this is what's important. Although these 2 things will not be linked together. The distance and delta theta won't be linked together because it's not rolling yet. I do know that one condition has to be met for them to be rolling. As the object slides to the right, the angular speed is increasing. In fact, the angular speed is going to equal this, right? That's how the angular speed is increasing. So the angular speed will be mr over I mu k g times t. The linear speed is decreasing. V final equals AT plus V initial, which for this problem, V final equals V initial minus mu kg. Everybody follow that okay? This number's getting smaller. This number's getting bigger. Yep.
Where did time go for the...
Oh, time should be right here. Sorry. But again, as time goes on, this number's getting bigger. This number's getting smaller, and this number's getting bigger. Right? Well, they're rolling when VF equals omega r times r. Omega f times r. That's when rolling occurs. If we find out how long it takes this times r to equal this, then that time is how long it takes until we're rolling. Everybody follow along? Because this, again, getting smaller, this is getting bigger, this is a constant. So I'm going to put those 2 things together. I'm going to say V naught minus mu k gt equals mr over I mu k gt times r. Now I'm going to reorganize this a little bit to make it neater. I'm going to put mr squared over I together and get my mu k gt there. I'm going to move this term over to the other side and get plus mu k gt, and leave V naught over there by itself. Everybody all good? Just doing algebra now, cleaning this up, but we're going to try and figure out that time. I hope you guys notice that we can factor some things out. We're going to get time by itself, so I would normally try and skip a bunch of steps. And this would be neater if we didn't leave it in terms of I, but we are, so I'm going to stick with that. And now solve it for t. This is how long it takes until we're rolling. This is not the answer. The answer was about how far it goes. This is how long it takes. Now, this looks way complicated, but remember, you're going to put something in for I, right? For example, we're supposed to compare a ring with a solid sphere. Pick one of them. The ring. So T for the ring equals V naught over mr squared divided by mr squared plus 1 mu k g. So T for the ring is V naught over 2 mu k g. T for the sphere, might as well, we're right here, right? V naught over mr squared divided by 2/5 mr squared plus 1 times mu k g. That's 5 halves. 5 halves plus 1 is 7 halves. So this will equal 2 V naught over 7 mu k g. You should probably check my arithmetic. It's getting late in the day, but I'm pretty confident in my stuff. But it's just arithmetic. It's nothing particularly complicated. So seems to me like one of them's going to take longer to get there than the other. Now, at this point, we can find the distance. We have time, but we want d, not delta theta. So you're going to need a relationship that gives you d. You have an expression for t. We know v naught is the initial velocity. We know acceleration is minus mu k g, and we want the distance. So I would probably say an equation that has all of those in it. So distance equals 1/2 a t squared minus v naught times t. Is that the distance? Looks good to me. I see a mu kg in the numerator here and a mu kg squared in the denominator there. So one of those is going to cancel out, but I also see the 2 squared. So I think all of this will be v naught squared over 8 mu kg and is negative. Plus v naught times v naught gives me v naught squared over 2 mu kg. So common denominators, this is 4/8, and 4/8 minus 1/8 is 3/8. So this will be 3 v naught squared over 8 mu kg. That's for the ring. A lot of algebra. A lot of algebra. When we did the problem in class, we didn't find the distance, we just found the time. And we did the problem in class, we did it for a specific shape, we didn't do it in terms of I. But we did the problem in class. Yes, this is more complicated. I wanted you to practice it. This problem has been on the exam before and in recent memory. So when I say recent memory, last 10 years. So it's been on the exam, and it comes back up every once in a while. It's complicated. They usually step you through it. They usually ask for you to find the time, and they usually ask for you to find the conditions when it'll be rolling. So they ask several leading questions, but this is a long one. There's a lot to do here. And I think it's interesting which one gets to rolling first. You should look at it and see if it makes reasonable sense. All right, so our object has a initial velocity of 10 meters per second and is rolling without slipping across a horizontal surface. It is a solid sphere, so it has moment of inertia of 2/5 mr squared. It's approaching a 25-degree incline. It's at a height of 3 meters, and it has a radius of 0.2 meters. Calculate the total kinetic energy of the sphere as it rolls along the surface. That's not particularly interesting. 1/2 m v squared plus 1/2 I omega squared. They don't give us omega, but it doesn't really matter. If we're going to do this the most simple way possible, we should probably put it all in terms of v. So I'll sub in the moment of inertia here of 2/5 mr squared, and then sub in v over r because we are told it is rolling. This will get the radius out of the problem, one less thing to worry about. The 1/2, the 2 and the 1/2 cancel, and we get 1/5 and 1/2, common denominator 10. So let's see, 10, is it 7/10 mv squared? I believe that's right. Can somebody check my math? Is that good? All right. So we have the mass, we have the velocity, so I think that part's done. That is the kinetic energy of the system as it's rolling along the surface. Calculate the magnitude of the sphere's velocity just as it leaves the top of the incline. When it makes to the top of the incline, if the incline has sufficient friction, then when it makes to the top of the incline, some of this kinetic energy is going to be converted to potential energy. That's going to slow it down. So at the top of the incline, it'll have kinetic energy plus gravitational potential energy. So it's still going to be 7/10 mv final squared because it's rolling and the shape is the same. Different final velocity, but plus mgh, where h is 3 meters. We can set these two things equal to each other in order to determine what the velocity is as it leaves the ramp. And it leaves at an angle of 25 degrees, so you now have a projectile. I don't really feel like doing the projectile problem. Do you need me to do that? Draw a little chart, figure out the time it's in the air and all that? I mean, I will, because you're asking, but it's an old problem. Let me know, because there will be projectile stuff on your next test. You can't really avoid it. Well, yes, I can. That's why I'm asking you, though, because I don't want to. I will when you tell me what this velocity is. You guys are untrustworthy. I know that in this problem, we will not need the mass. It will cancel out. Untrustworthy. The fact that this is all we're talking about and there are 5 different answers thrown around in the room, that's just sad. So cancel out one of the 10s there, and this is 70 equals 7/10 VF squared plus 30. So 40 equals, why not? Why 40? Let's just go ahead and do more math than that, because what do you care? 40 times 10 is 400 divided by 7. So 400 over 7, and take the root. That's what we're looking at, whatever the answer to that is. But again, I would go 2 decimal places or more if this is going to be an actual FRQ, especially since there's going to be a projectile portion to the problem. Now, as there is a projectile portion to the problem, I still go this way for them to organize myself. It's also a reminder. So the vertical side is going to have a y displacement of -3, an initial y velocity of 7.56 sine 25, a acceleration of -10 meters per second squared, and I need how long it's in the air. So that's a job for you guys, but not really, because we know what you guys do here, but we need the time that it's in the air. And in the horizontal, I'm looking for the range, but Vx is going to be 7.56 cosine 25, and time is going to be whatever we get over here. And the range will be Vx times t. I'm so not interested in that question that that's as far as I'm going to take it. Although you asked for me to go a little bit further, this is all I feel like I have the patience to do. Okay? Not because I'm not patient with you, it's just that this is kind of pedestrian stuff. Practice your projectile motion. This is just math. Okay? And there's so many mathletes in the room, this shouldn't be a problem, right? Suppose instead the sphere were to roll toward the incline as stated before, but the incline were frictionless. State whether the speed of the sphere, just as it leaves the top of the incline, would be less than, equal to, or greater than the speed calculated in B. Briefly explain why. It's going to be less than. For one, the frictional force is up the ramp. You could do it by forces, and since there's no force pushing it up the ramp, it's going to be traveling slower. We'll explain why the frictional force is up the ramp in a minute. But also without friction, there would be nothing to take away any of the rotational kinetic energy, which means it'll have the same rotational kinetic energy at the top of the ramp as it has at the bottom of the ramp, which means all of the energy that goes to gravitational potential had to come from the translational kinetic energy, which means it'll have a smaller linear velocity. So it'll be moving slower and won't travel as far. Those are both reasonable explanations. So now let's handle the problem that apparently Yimo's having with the direction of friction. And we'll keep it consistent with the direction of the problem before. So something like this. And I'm going to ask what I hope is a reasonable question, Yimo. The object has a rotational speed in this direction when it first meets the incline. Is the rotational speed going to increase, decrease, or stay the same? So from the point where it starts there to the point where it is, say, I don't have to go too much further, but let's say a little further. Its rotational speed will have decreased some. Now, if we assume we're considering all torques relative to the center of mass of our rotating shape, what direction would the frictional force have to act to cause a torque to reduce the rotational speed? It would have to be up the ramp. Oops. So there would have to be a frictional torque this way up the ramp. Now, the truth is, we've talked about rolling a couple of times. And one of the things about the ramp is that we can take into account either the pivot point being at the center or the pivot point being at the point of contact. If it's the pivot point being at the point of contact, we still have to make the argument that friction has to be up the ramp. And the reason for that is if the pivot point's at the point of contact, which is a fair way to consider the problem, that point has to not move with respect to the ramp. Meaning the sphere or the ring can't slide at that point, at this point, instantaneously at this minute. We know we have a force down the ramp due to the weight. The only way that point can stay there is that the net force at that point is zero, which means there has to be an upward force to balance the component of the weight down the ramp. It's the only way for this point to be, it's the only way for this, oh my word, Mr. Shelton. It's the only way for this point to be instantaneously not moving with respect to the ramp. Now, I like the argument from the center of mass perspective that the frictional force is necessary to reduce the angular speed. I like that argument better because it's kind of the way I visualize the problem in my own head. But either argument has to successfully explain why the frictional force is up the ramp. But also consider this. Do you buy into the argument as to why, if it were frictionless, it would be traveling slower at the top of the ramp when we talked about it using energy? Did that make sense to all of you? Well, Newton's laws and energy are cooperative laws. Newton came up with both of them. and one is derived on the back of the other. So the only way the object could be going faster at the top with friction is if friction was pushing it up the ramp. And that's literally what's happening. The object has inertia. So you can imagine that it has traction against the ramp. It is that friction and the fact that it has traction that is helping propel it up the ramp. I am sure when you were a child, well, maybe not. Maybe when you were a child, you were weird and didn't play with toys. But there was probably at least some point where you took something, spun it in the air, and watched that when it hit the ground, it would take off. Well, what made it go? What made it go forward? The only force that would be acting forward on it was friction. Right? Do you know the situation I'm talking about? I mean, I've tried this problem 3 different ways over the course of the day, and it's always last on every one of the videos that I'm going to post. It got a little bit messy because of questions asked in 6th period, but it was very clear in 3rd period. I'm doing a more traditional version of this problem in your class, okay? I want you to imagine we're looking top down on a horizontal frictionless surface, like an air track or an ice hockey court or something like that. But let's assume that that's a level surface. And on that surface, there is a just something simple, a simple shape, a rod, and a puck. Now, I want you to consider a collision between these two. Hello, I didn't bring it. It was, I'm sorry, I should have told you, it was pouring this morning. If this is on an ice sheet or something that's frictionless, then I want you to imagine what would happen if the puck struck the rod and then recoiled off the rod. Like, let's say that the rod has mass m, the puck has the same mass m, is traveling at v towards the rod, strikes the rod, and recoils at 1/2 of v. In this case, the rod isn't affixed to anything. It has no fixed pivot point. So this is not only a linear collision, meaning the rod's going to have a motion of its center of mass after the collision. But it's also, because it's offset, the puck has angular momentum before the collision. And therefore, the rod's going to have angular momentum after the collision. This is, I think this is a more interesting question than the ones we've seen. The fixed pivot point means that the linear momentum of the system is negated because there's an external force that ensures that the object that is struck doesn't go anywhere. But in problems like this, that doesn't exist. Now, the collision part of it, the linear collision part, isn't that big a deal. The momentum of the system before the collision is mv. After the collision, the momentum of the system is going to be m times negative 1/2 v plus mv final for the rod. That's going to be the linear momentum. This will tell us the velocity of the motion of the center of mass. However, there's angular momentum. So although this will tell us how fast this part is going, Vf, we're also interested in omega for the rotational rate of the system. That's a little bit harder, and it's not terrible. I want you to remember that if an object doesn't have a fixed pivot point, it will naturally rotate about its center of mass. So since we know where the center of mass is, we know that the angular momentum of this puck will be based on the point of closest approach, which we talked about when it comes to the motion, the angular momentum of a point mass. So its angular momentum would be just the angular momentum of the puck, which will be r perpendicular times mv, or in this case, L/2 times mv, where L is the length of the rod. Good so far? Not terrible? Well, after the collision, the rod has angular momentum, I times omega, and the puck still has angular momentum because it bounced back. Now, yeah, if I want to find the angular speed, I'm probably going to have to put in something for the moment of inertia of the rod. I'm pretty sure that this is going to have something to do with how fast the puck was going originally. Not particularly terrible, is it? Now, I'm going to give you a practice like this over the weekend. It's a practice test. I'm probably not going to post it till later tonight, but I'm not going to make it due till Monday. But it's just a practice test. We're going to go over it on Monday. This problem becomes much harder if the puck sticks to the rod. If you're taking notes, think about it. If the puck sticks to the rod, in the old days, first semester, when we talked about conservation of momentum questions and things stuck together, it generally made them easier. But when the puck sticks to the rod, it shifts where the center of mass of the system is, right? Which means your original angular momentum has to be based on the new center of mass. So meaning you have to know what the center of mass is going to be before the collision even takes place. And you also now have to shift the moment of inertia to the new center of mass because that's the point about which it's going to rotate. So if it sticks to the rod, that makes for a tougher question, a more complicated question. It bouncing off the rod, not so terrible. And if you did the problem that's in the homework that's like this is similar. This is a very similar question, except that it has the fixed pivot point. And that fixed pivot point makes it different than this problem. All right, that's enough for today. As I drew it here, the center of mass is shifted to here. That makes this new distance, wherever the center of mass is, you have to find out the center of mass. You have to calculate it by using the center of mass formula. But that also changes R perpendicular for when you calculate the angular momentum. But then also you'll have to use like the parallel axis theorem to shift to the new position. Well, it's not R perpendicular here, but to shift to the new position. You follow me? All right. That's what you have to do. Bye-bye, folks. Have a great weekend.